So limitations today is 2 to 22. Very typical day. 2. So first of all, intrinsic charge carrier concentration is low. Intrinsic charge carrier concentration is low, of the order of 10 to the power 6 per meter cube. Low electrical, so having low electrical conductivity. Secondly, all the charge carriers are thermally generated, hence no control over the carrier concentration. And thirdly, Ne is equals to Nh, limits the usefulness of such material, because here you do not have any predominant current. Current for electronic current, same electron density, so there is no predominant hole or electrical electron conduction. So this puts limits of the usefulness of this material. That is why we go for the doping. Now, what is doping? The process of deliberate addition of a desirable impurity to a pure semiconductor so as to increase its conductivity is called doping. Okay, the process of deliberate addition of a desirable impurity to a pure semiconductor so as to increase its conductivity is called doping. So it is a deliberate addition of a desirable impurity. So always impurity are not bad. In this case, at least in this case, that addition of impurity increases the conductivity than the pure one. Okay. So the impurity atoms is called dopant. Is the impurity atom. It's called dopant. The semiconductor doped with impurity atoms is called extrinsic or doped semiconductor. The semiconductor doped with impurity is called extrinsic or doped semiconductor. So as I discussed earlier that in general, uh, we take either pentavalent dopant like arsenic, antimony, phosphorus for creation of N-type semiconductor. So arsenic, antimony, phosphorus, etc. for creation of N-type semiconductor. Otherwise, we will use trivalent dopant like indium, aluminum, etc. for creation of P-type semiconductor. Now, we just study the thermodynamic relation between the number densities of electrons and holes in case of doped semiconductor, obviously. Now, when conduction electrons and holes are created in a semiconductor, the process of destruction occurs simultaneously. Okay. So, when conduction electrons and holes are created in a semiconductor, process of destruction occurs simultaneously. Destruction means recombinations. Destruction means here destruction means recombination of electrons and holes. As electrons and holes pair are generated, also they can recombine. Now at equilibrium, the rate of generation of charge carrier is equal to the rate of recombination of charge carrier. At equilibrium, rate of generation of charge carrier is equals to rate of recombination. So how many electron and hole pair are generated? Same number of electron and hole pair will recombine each other. Okay. At equilibrium, initially the rate of generation is higher than the rate of recombinations, but at steady state, rate of generation and rate of recombinations are same. Now, larger the value of the number density of electrons and holes, higher is the probability of their recombinations. Large Ne or NH, higher is the probability of recombination. Okay, so as the number of electrons and holes will become higher, then their recombination probability will also become higher. Okay, hence intrinsic semiconductor rate of recombination in intrinsic semiconductor rate of recombination is proportional to Ne into NH. That means rate of recombination equals to some constant R into Ne into NH. This R is known as the recombination coefficient. Recombination coefficient. Now for intrinsic semiconductor, Ne equals to NH equals to Ni for intrinsic semiconductors. Okay. Now, as long as the lattice structure of the semiconductor remains same, the value of R, the rate of recombination or the rate of generation, which are governed by the laws of thermodynamics, remain the same. So as long as the lattice structure remains same, the value of R, that is the rate of generation or rate of recombinations, remains the same. Hence, the rate of recombinations hence R into Ne into NH is equals to R into Ni square, or Ne into NH equals to Ni square. True for doped semiconductors also. So this is a very important questions for semiconductor physics, which implies the following facts. Once for N-type semiconductor, Ne is necessarily greater than NaH, yet its product with NH remains Ni squared. For N-type semiconductor, Ne is greater than NH or Ni, but Ne into NH equals to Ni square. This implies that number of holes get suppressed in N-type semiconductor. Number of holes get suppressed in N-type semiconductors. That means some of the thermally generated holes are destroyed due to recombination of process. Similarly, for P-type semiconductor, for P-type semiconductor, NH is greater than Ni, against Ne into NH is equals to Ni square. Hence, Hence, the number of electrons get depressed. Suppressed, sorry, in a p-type semiconductor. So number of electrons will get lower in p-type semiconductor, while number of uh, holes will become lower in n-type semiconductor. Okay, just give me a moment. Just a moment, please. Now we have to know a little bit about energy bands in solid. How the energy states of individual atoms, how the energy states of individual atoms changing into energy bands. That we will discuss about that basically, how the energy states is changing in bands. Just a minute. Now let us consider a small single crystal of silicons. Consider a small single crystal of silicon. So what is happening basically, when enormous large number of energy bands are closely spaced in a very small energy range, they constitute energy bands. What is energy bands? When enormous, enormously large number of energy states, enormously large number of energy states, energy levels, sorry, closely spaced in a very small, in a very small energy range constitute an energy band. Sorry for disconnection for a few minutes. Energy bands in solids, energy and so what is energy bands? When some huge number of closely spaced energy levels are spaced in a very small energy range, we constitute energy bands. So from Bohr's atomic model, what state? Bohr's atomic model, we know that the electrons have definite energy states. Energy levels in an isolated atom. But due to interatomic interaction in a crystal, the electrons of the outer cells are forced to have energies different from those in isolated atoms. Just a minute.
Sir, you're on mute.
So according to Bohr's theory, Bohr's atomic models, electrons have definite energy levels in an isolated atom. But when these atoms are placed in a crystal due to interatomic interactions, the electrons of the outer cells are forced to have energies different from those in isolated atoms. Now, each energy levels splits into a number of energy levels forming a continuous band, which is called energy band. Continuous band, which is called energy band. Okay. So what is happening? There are different energy levels. Now, when two atoms close together, the outer cell energy levels are splits. They are one energy levels like this. Now they have splits. Now they come close together so that they will form like a semi-continuous uh, energy levels, energy bands. Okay. So here, these energy states are very close to each other. It is, and they are placed in a very small energy range. So they are basically create some energy bands. Now let us consider the case of a single crystal, silicon single crystal. Now when the atoms are brought closer from infinity as to form the crystal to the lattice spacing, which is 2 to 3 angstrom. So this is depicted, let us draw one picture. There will be a pictorial demonstration. So what are just picture is not very clear. Yeah. 1s2, 2s2. Now in crystal, each electron has its unique positions and no two electrons uh, can have exactly the same positions, and no two electrons see now cannot see exactly the same pattern of surrounding charges. Because of this, each electrons will have different energy levels. Now these different energy levels with continuous energy variation from what I call yes. Say this is the just energy levels. It is n minus 1 cell. This is L equals to 0. Say if 3 is for selection the silicon outermost orbit is 3. So N minus 1 is 2. L equals to 0 is 2s. L equals to so you will have 2s and 2p. L equals to 1. It's 2p. Okay. And also you have init energy levels, that is the third one, that is 3s, 3p, 3g, like this. This is the nth level. This is L equals to 0. This is L equals to 1. Okay. So this is the nth cell. Now when they come closer, then after certain distance, there will be a splitting of energy levels. And there will be overlap of energy levels. Then again, after certain distance, this overlapped energy states will split and give rise to what is called the band gap. And it is happens at the lattice spacing A. Okay. So let us explain it a little. So this is energy, and this is in this case lattice distance. Separation between atomic separation. Okay. Now, what is happening? Basically, if we consider the case of now this band, this is becoming conduction band, and this is becoming the valence band. And difference between these two will give you the energy band gap. So this is valence band and this is conduction band. Okay. Now let us consider this. The situations. One, R is then the separation D is much greater than A. A is the interatomic separation or spacing of the crystal. So what is happening at the large at this interatomic spacing, there is no interaction. There is no interaction between the atoms. As there is no interactions, you can see these energy levels are separated as if they are similar to that of the isolated atoms. Okay. So when the distance of separation is large, then the energy levels are similar to that of the isolated atoms. Okay. Now all the n atoms have identical energy levels. All the n atoms have identical energy levels of the outer cell. Now, in energy level associated with the outer cell are completely filled with 2n electrons. In energy levels are associated with outer cell are completely filled with 2n electrons, because each energy level associated with out of energy level associated with 3p orbitals, only n levels can be filled with 2n electrons, and the remaining levels are empty. So if we consider the case of silicon, say, what is the charge in case of silicon? Now, what are the number of electrons in silicon? Fourteen electrons. Okay. So silicon 14, it is has 1s2, 2s2, 2p6, 3s2, 3p. So it will be 3s1, 3p3, like this. 2s2, 2p6, 3s2, 3p. Because of half filled orbit. Energy states of silicon. Yes. Minus 2, 2s2. So in the outer cell, we have 4 electrons. Now we have total of 6 plus 2. And we have 8 positions, 8 electronic positions. But we have 4 electrons in the outer cell. Okay. In case of silicon, in case of germanium, the outer cell is 2. Also, you will get 4 electrons in 2p and in 2s and 2p. That means here also, in case of germanium, in the outer cell, you have 4 electrons, but 8 electronic positions. So for single atom. Okay. Now here we have n atoms. So the outer cell has 4n electrons, 2n electrons are in 2n S cells. It's in 2n S sites, S states. With L equals to 0 orbital quantum number, and the 2n electrons rest 2n electrons are in 6n p states. So 1 is to 2 is to 2p6, 3 is to 3p2. This is the electronic configuration. 1 is to 2 is to 2p6, 3 is to 3p2. So here you have 6 states, electronic states, but there are 2 electrons. And you have 2 electronic states and you have 2 electrons. So for n atoms, you will have 2n s states filled with 2n electrons and 6n p states filled with only 2n electrons and empty 4n p states. Now, so in the outermost orbit, there are total of 8n states, 2ns plus 6n p states, and 4n electrons. Now suppose this atom starts coming closer to each other. Suppose these atoms start coming closer to each other. These atoms are coming closer to each other. Okay, coming nearer to each other. Okay, to form a solid. Our aim is to form the solid. Now the energies of these electrons in the outermost orbit may change, both increase or decrease. When these atoms are coming closer, becoming nearer to each other, just a minute, hold on. When these atoms are coming closer to each other, the energy of the outermost electrons outermost orbit, energy of the electrons in the outermost orbit may change. It may decrease or increase. We will see that energies of some of the electrons will get decreased and some of the electrons will get increased due to the interaction between the electrons of different atoms. Due to interactions between the electrons of different atoms. Now, the 6n states for L equals to 1, which originally has identical energies in an isolated atom, spread out to form an energy band. P level. In P level, we have 6n energy state, 6n states for L equals to 1, P states. Originally, having same energy, now spread same energy in an isolated atom. Now spread in now spread out and form energy bands. See that figure. L equals to 1. This is single energy level. Now they are spread out to form energy bands. Also, the L equals to 0 level are spread out to form energy bands. Okay. When they are coming closer to each other, the atoms are coming closer to each other. Similarly, the 2n state for L equals to 0, that means S states. Originally having same energy in an isolated atom, now spread out to form energy bands. Now at still smaller spacing, at still smaller spacing, that means when the spacing, we are reducing the spacing more. Here, the energy levels are fast spread out, but they are separated from each other. But when we are go close enough, more closer to each other, there comes a region in which the bands merge with each other. At still small spacing, their comes a region in which the bands merge with each other. Go to the figure. Here they are spreading, but they are separated from each other. Now here in this region, they merged together. They merged together. This is one, this is another. But in this region, they have merged. These are in this region, there is a merger region. Okay. Now the lowest energy states that is in that is a split from the upper atomic level appears to drop below the upper states. Let's go to the figure. Here you can see this is the lowest state in the upper level, and this is the highest state in the lower level. Now they merge together. They enter the this lowest energy level of the upper state merged into the highest energy level, overlapped with the highest energy level of the lower state. The lowest energy level of the upper state overlap with the highest energy level of the lower state. So that is, there is a now in this region, after this region, basically, in this region, you can see this is this region, there is no energy gap. Before we have an energy gap, but when this merger is there, there is no energy gap. Okay. No energy gap in this region. Finally, if the distance between the atoms further decreased, when the distance between the atoms decreased further, the energy bands again splits apart and are separated by an energy gap. Energy bands splits again and are separated with energy gap. E.g., the total number of available state energy states 8n, total number of available states are 8n, has been split into two bands. Foreign state each in the lower and upper energy level. Foreign states each in the upper and lower energy levels. Say in the upper level you have foreign states and in the lower level you have foreign states. This is the upper level. Here you have foreign states. In the lower level you have foreign states. Now the foreign states of the lower level are filled with foreign available electrons. Foreign states of the lower level band is filled with foreign available electrons. So all the states are filled, and this is known as valence band. And also the foreign states of the upper level filled at 0K. Foreign states of the upper level band are completely empty. At 0K and is known as conduction band. So in valence, why it is called valence band? Because these foreign states are filled with foreign valence electrons. Available valence electrons. Foreign available valence electrons. And the upper states are completely empty. If some electron goes into the upper states, then it will participate in the conductivity. So therefore, the lower bands are called valence band and the upper bands are called conduction bands. So if we draw a simplified picture, there are foreign states. You will have foreign electrons. The highest energy of this level is EV. And there are foreign empty states with lowest energy EC. And the difference between these two is EG. This is called band gap. So what is band gap? The energy difference between the lowest energy level of conduction band and the highest energy level of the valence band. So energy difference between the lowest energy level of the conduction band and the highest energy level of the valence band is called energy band gap. Now, when this energy band gap, this is conduction band, this is valence band, this Eg is greater than 3 eV, then it is called insulator. So the present definition is slightly different. I'm going to that. But when this energy band gap is less than 3 eV, then it is called semiconductor. And what is conductor then? When there is no band gap between this is EV and this is EC. That means there is a overlap. Eg is 0. This is conduction band. Actually, in case of overlapping of conduction and valence band. So this is the case of conductor. This is the case of conductor. Now at absolute zero, this valence band is completely filled. And this conduction band is completely empty. So there will be no conduction. And semiconductor will behave as insulator. So what is the conductivity of a semiconductor at 0 Kelvin? What is the conductivity of a semiconductor at 0 Kelvin?
Is it 0?
Yeah, it is 0. Conductivity of a semiconductor at 0 Kelvin is 0. So at 0 Kelvin, semiconductor is behave like a insulator. So this is the difference between semiconductor, insulator, and conductor. So band gap wise, there is no difference between insulator and semiconductor except the value of energy band gap. Band structure of insulators and semiconductors are nearly same except for the energy band gap. In case of semiconductor, these energy band gaps are very small. Up to 3 eV, they are called semiconductor. Above 3 eV, up to 5 eV, they are called wide band gap semiconductor. And above 5 eV, they are called insulator. But for your knowledge up to this level, just remember below 3 eV, they are insulator. Above 3 eV, they are below 3 eV of band gap, they are semiconductors. And above 3 eV of band gaps, they are insulators. Okay.
Yes, sir.
Now, in case of intrinsic semiconductor, energy bands of intrinsic semiconductor. Is pure. So at 0 Kelvin, there are empty states in conduction band, and there are completely fielded states in valence band. And this gap is Eg. This is in energy. This is electronic energy. We are measuring electronic energy. Okay, which is at 0 Kelvin. So all the electronic states are fielded in case of uh, intrinsic semiconductor at 0 Kelvin. Now, when the temperature increases, when T is greater than 0 Kelvin, some of the electrons will jump. So you will get some holes here, and these 4 electrons say gone here. So these electrons got some energy so that they can jump into the conduction band. Now, here they have plenty of empty positions so they can move. And also these holes, they can move in the valence band. So now they will participate in the conductivity. In these situations, there is no states where the electrons can move, and there is no electrons. There are plenties of states, but there is no electrons. There are plenties of electrons in valence band, but there is no empty states where the electrons can move. And in conduction band, there are all the states are empty, so there is no electrons, although they have plenties of state, but no electrons to move. So there is no conductivity at 0 Kelvin, no conduction of electricity at 0 Kelvin. But when we go above 0 Kelvin, some of the electrons will get thermal energy so that they can jump into the conduction band. So here these electrons will find some empty space so they can move, and also these holes will also move in the valence band. So they will participate in the conductivity. So this is the case of intrinsic semiconductor. Now let us consider the case of N-type and P-type semiconductor. Now in case of N-type semiconductor, you are giving a donor level. We just one electron, N-type semiconductor means we have doped with pentavalent. One electron is nearly free. That means it is very close to the conduction band. So this is here we got a donor level. This is EC, this is called ED, and this is my EV. So this gap is of the order of 0.01 EV. This is my band gap. This is huge, but here the gap between the donor level and doping with pentavalent atom will introduce a donor level very close to the conduction band. Hence, so the electrons from this donor level can jump into this conduction band. And also some thermally generated electrons are also there. So here, number of electrons is greater than the number of holes created in the valence band. So number of electrons in the conduction band is greater than number of holes in the valence band. So you can see that the electronic conductivity is more than the hole conductivity. Which dominates over the whole conductivity. Electronic conductivity dominates over the whole conductivity. So this doping will create an energy level very close to the conduction band. This level is called donor level. And so electrons can easily, from the donor level, can easily move to the conduction band than the electrons from the valence band, because here the energy difference between the valence band and conduction band is quite high compared to the energy difference between the donor level and the conduction band. So number of electrons in the conduction bands will be much higher than the number of holes in the valence band. So here the majority charge carrier is the electrons. So electronic conductivity dominates over the whole conductivity. Similarly, so it is the case of N-type. In case of P-type, what is happening? The doping of trivalent element, basically, you will have a vacancy there which can accept one electron. That means they are creating a acceptor level very close to the valence band. So EA, EC, EV, this is your valence band. This is your conduction band. This is called donor level, and this is called acceptor level. So what is happening? Some of the electrons can go easily to this acceptor level. Some will go to the conduction band also. Now you can see the number of electrons in the conduction band is much lower than the number of holes in the valence band. So doping with trivalent atom will introduce an acceptor level this difference is very small, of the order of 0.01 ev, close to, and whereas this difference is huge, this is eg. very close to the valence band. So number of electrons in the conduction band is much smaller than the number of holes in the valence band. Number of electrons in the conduction band is now much smaller than the number of holes in the valence band. So here the hole conductivity dominates over the electronic conductivity. Okay. So this is the case of the energy band diagrams of different semiconductors. Just go through the difference between intrinsic and extrinsic semiconductors. I will stop here today. In the next class, we will discuss about mobility of charge carrier, electrical conductivity in a semiconductor, effect of temperature in conductivity, and also we will discuss about application of semiconductor as PN junction diode and application of diode in various purposes, characteristics of diode and application of diode in various purposes. I think in the next class we can finish this chapter. Okay. So thank you for
Okay,
today.
sir.
Okay.
Thank you, sir.
Thank you.